In this video, we're going to be taking a look at the multiplication of two functions as a way to find the Taylor series for a function that is a little bit more complex. We'll be using example 5.9 from your course pack, and the function we're given to find the Taylor series for is this one here, e to the x over 1 minus x. And I hope you recognize right away that I can write f of x as e to the x times 1 over 1 minus x. And we know the Taylor series for e to the x, and we know the Taylor series for 1 over 1 minus x. So let's see how we can use that information to find the Taylor series for the product of those two. Well, e to the x, let me write it up here. E to the x is equal to its Taylor series, the sum, as I goes from 0 to infinity, of x to the I over I factorial. So what I've just done, and I'm going to multiply this now, what I've just done is I've rewritten e to the x as its Taylor series, as this summation. And now I'll rewrite this expression using its Taylor series. That's just the sum, as I goes from 0 to infinity, of x to the power of I. So that corresponds with 1 over 1 minus x. Now, in this case, because I'm trying to demonstrate where the sort of formula that we're going to use for these comes from, I'm going to take a moment and write out the first few terms of the Taylor series for e to the x. I'm going to get x to the power of 0 over 0 factorial plus x to the power of 1 over 1 factorial. I think I'll do 5 terms. X squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial. Of course, that goes on forever, but to that, I'm going to multiply, or with that, I'm going to multiply the first 5 terms of the Taylor series for 1 over 1 minus x. I have x to the 0 plus x to the 1 plus x to the 2 plus x to the 3 plus x to the 4. And that one goes on forever as well. Now, if I were actually going to multiply these, I'd be taking this term here and multiplying it by all of these, and then this term and multiplying it by all of these, and so on. So I'm not going to do all of those, but I'm going to do the first several, 2, maybe 3, just to see what the pattern is. I'm also going to start over here because I know I'm going to run out of room otherwise. All of this is equal to, actually before I do that, let's go back and tidy this up a little bit. X to the power of 0 is 1, and 0 factorial is 1, so this is 1. Then I have x to the power of 1 over 1. Then I have x squared over 2 factorial. So that's a little bit easier to work with, especially for the first few terms. X cubed over 3 factorial. And I'm going to tidy up this other one as well. I have x to the 0 plus x to the 1 plus x squared, and so on. All right, now I'm going to go over here, and I'm going to multiply this term times all 5 of these terms. I'm going to get 1 plus x squared plus x cubed plus x to the 4th. And to that, I'm going to add x times all of these terms. So underneath, I'm going to write this as a sum. So underneath here, I'll have, right, the next, maybe at least two series from this. I've done the 1 times all of these. Now I'll do x times all of these, and then I'll do this term times all of these. We'll see if that's enough. It might not be. So I'm multiplying x by everything in the second group of terms. So x times 1 is x times x is x squared, x times x squared is x cubed, x times x cubed is x to the 4th, x times x to the 4th is x to the 5th. Now I'll multiply this term times all of these. I have x squared over 2 factorial times 1 There should be a plus there. Plus x squared over 2 factorial times x, and so on. I think I want to do one more set. The next one is x cubed over 3 factorial times 1 times x 2, x squared, and so on. So we end up with this for our next series. And now if I add all of these together, I get 1 plus 2x plus, now I'm going to factor out the x squared here, and that leaves me in this column right here, leaves me with 1 plus 1 plus 1 over 2 factorial. That's a constant. It's 1 plus 1 plus a half. Let me highlight that as well so we remember where that came from. Then in the next column, I'll use a different color highlighter. I'm going to factor out the x cubed. I get x cubed times 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. And that matches my yellow column. I'll do the same thing for each of the next few terms. Actually, this next one is, I could add here another obvious term. That next term there is just going to be x to the fifth. So I'll add that one. And then I'll have two more columns. I can do x to the fourth and x to the fifth over here, and I'll leave it at that. We'll have, the pattern will continue, but we'll have enough from that, from the first, 1, 2, 3, 4, 5, 6 columns. That's plenty. We'll have enough from those first 6 columns to see what the pattern is. So I'll just write those out, and I'll come back in a second. So when I add up this column, factoring out x to the fourth, I get x to the fourth times 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. And when I factor the x to the fifth out here, I get x to the fifth times 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. Notice, however, that not only does this pattern continue in this direction forever, but it also continues in this direction forever. So in addition to my 1 over 2 factorial here, and then a 2 and a 3 here, I should have a 2 and a 3 and a 4 here. And I should have a 1 over 4 factorial and a 1 over 5 factorial here. So that pattern is also continuing. So now each one of these big terms here, I have this blue one from the x to the fourth column, I have this white one from the x squared column, this pink one, including this stuff up here, from the x to the fifth column, and so on. Each one of those has this pattern: 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, for as many terms as there are in that particular thing, right? Also, remember that 1 can be written as 1 over 1 factorial, and it can also be written as 1 over 0 factorial. So if I want to make the pattern even more obvious, I can do that. This is the sum, as I goes from 0 to infinity, of 1 over I factorial. Now I kind of want to hold this in reserve for a moment. Is this really going to make me move one term at a time? No, thank goodness. Okay. I'm going to hold this in reserve. So I'm going to put a box around it, because this is a piece that we're going to need in a minute. But I also need to make the observation that each one of these terms also has this leading x factor in it. This is x to the 0, x to the 1, x to the 2, x to the 3, and so on. So I also have x to the 0, x, I don't want to put pluses in there. Well, I kind of do, because these pluses here indicate that each one of these is getting added. But it's not, they're not getting added in the same way. Let me erase that plus there. That's a little confusing. X to the 1, x to the 2, x to the 3, and so on. So one thing to notice here is that I'm adding a bunch of terms together, right? And each one has an x in it, but each one has an x to a different power. So I need to somehow write the sum of all the x to the, I'm going to use a different dummy index here, the sum of all of the x factors times the sum of all of the factorial factors. The problem is that each term has x to a power, and then each term has a sum like this or this of the 1 over factorials. But each time you change this index, each time you change the exponent here, you also add another term down here. So it gets a little confusing. I can't just say, I'm going to put this in a different location. I cannot just say that this is I goes from 0 to infinity of 1 over I factorial times the sum. Oh, having trouble with my sigma for some reason this morning. There we go, that'll do. As I goes from 0 to infinity of x to the I. Because this would just be, the third term here would be 1 over 3 factorial I cubed. And that's not what we have. For I cubed, we have, for I equals 3, we have x cubed times all of this. This 1 over 3 factorial is definitely here, but I also need the sum of 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, and 1 over 3 factorial. And that's not represented here. So I need to find a different way to indicate that this thing here is adding a term for each value of the index that's one higher than the one before. And the way we're going to do that is we're going to say, so let me cross this out because we're not going to do it this way. This does not work. What we are going to do, I'm going to erase this now because it's the only place I have left to put my result. But keep in mind that I'm kind of trying to use these two pieces of information in a way that will get me to a single, not a single summation, but a single expression. All right. So let me get rid of those. And then I'll add in the sum, and I'm going to leave the indices off. And another sum here. And I'm going to put my 1 over I factorial in here, and I'm going to put this in brackets. So what I'm saying here is take the sum of 1 over I factorial and do that for values of I that start at 0, because that is where we started here. Where am I? Oh, I erased it. In any one of these, right? Let's take this one, for example. We have 1 over 4 factorial, 1 over 3 factorial, 1 over 2 factorial. We decided to write this as 1 over 1 factorial, and this one is 1 over 0 factorial. So even in this first term here, where I has a power of 0, the x to the I is 1, and 1 over 0 factorial is 1. It's in there. We just can't kind of see it in this form. It's sort of this piece right here, right? So I want you to do that now from I equals 0, starting at I equals 0, but we're only going to go up to k. And the reason for that is that for every instance of a new term, we're saying go up to this number here, 4 in this case, and stop. For that term, stop at 4 here and stop at 4 here. So for just this term, I'm saying I equals 4, and that's where we're going to stop. For this term here, I equals 5, we're going to stop at 5. Way back here for this term, I was 2. But we don't want to stop at 2 or 4 or 5. We want to keep going. The thing is, we have to, for this term, we have to stop at whatever term we're in, right? This is our 6th term, so we stop at 5. We start counting at 0, and we stopped counting at 5, so that's our 6th term. So we have to put a limit on, for this term, how high we can go when we're using, when we're adding up our 1 over n factorial, 1 over I factorials, right? Now, having set that limit on each individual term, what I want to do is, I don't think I'm going to be able to get away with just moving this. Oh, I am. What I want to do is add up all of those terms and multiply the result I get from this for whatever k happens to be, right? I can start at 0 and end at 4. I can start at 0 and end at 9. I can start at 0 and end at 3. But for each instance here, I want to take all of those terms and multiply them by x to the power of k. Where I stopped here, I also want to stop here. Let's use this term here as an example. This x to the k is going to be the x to the 4th. This summation here is 1 over 0 factorial, 1 factorial, the sum of those, and 2 factorial, and 3 factorial, and 1 over 4 factorial. That sum of terms up to 4 times x to the 4th power. That's what that is there. Now, we're going to take k, and we're going to start at 0, way back here. When k is 0, I get x to the k, x to the 0 is 1, and I get 1 over 0 factorial, which is 1. 1 times 1 is 1. So I get just 1. We're going to start at k equals 0, and we're going to go to infinity. So here I have 6 terms. So I went from 0 to 6 for k, but by adding this piece on the outside, I'm saying, you know, go as high as you need to for k, but then stop. Whatever k is, use that number here, stop at k down here, then for k, go from 0 all the way up to infinity. This is a hard idea to get your head around, and your course pack, I think, doesn't do a very good job of explaining why it sets out this notation the way it does. And so I'm hopeful that my explanation has added a little something to what it says in the course pack, why this notation works. So this is my result. This is my answer for this question, the one in green here. And there's a website. It's math.pitt.edu, and I'm not going to list the whole URL here, but I'll tell you how I got there in just a second. It also gives kind of a formula, and I think I like the formula a little bit better than the explanation given in the course pack. The course pack talks about just multiply the two series together, so to speak. It's not really quite what we did, but then ignore the powers of x higher than n, and that doesn't really make sense either. So let me give you this formula. I think I'll do it on a new screen though. So remember this result, that the Taylor series for this expansion, or sorry, for this expression, for this function, was not necessarily, it was not just the Taylor series for one times the Taylor series for the other. What we can do, and I'll show you on the next screen, is we can write f of x times g of x is equal to the sum as n goes from 0 to infinity of a new function h sub n of x minus b to the power of n, where the function h sub n is equal to its own sum, going from k equals 0 all the way up to n, but only n, not infinity, of f sub k times g sub n minus k. And if we use this to build the Taylor series for e to the x times 1 over 1 minus x, we'll recognize that, first of all, that e to the x is my f of x, and I have f here in my formula, and g of x is my function 1 over 1 minus x, and that's this g of x here. All right, now let's find, using the formula, I'm going to have that this is equal to the sum for as n goes from 0 to infinity. I should point out that I'm using different indices here, n and k, than I did in my example, primarily because this is how it's written on the website that I found this on. And when I tried to use I and K instead of, I just got really confused and I kept messing up which index I was using where. So I just copied it from the website. But let me show you how this works. H, so now I'm going to take the sum of the function H, right? And the function H is itself a sum. So what I've done so far is I've copied down the summation as n goes from 0 to infinity. And now what I'm going to do is build H of x minus b. Now our b was 0 because we were asked to do this based at 0. So that makes that a Maclaurin series. So I'm just going to have x to the n here. But I'm taking the function of h, which is looks like this. So let me put h in a new color. I think I'll do pink. H sub n evaluated at x minus b to the power of n is all of this, right? It is itself a sum. So I'm going to have the sum of the sum, as k goes from 0 to n, of the function f evaluated at k, and k goes from 0 to n. So evaluated at k, and the summation for e to the x is x to a power over that same number power factorial. And we're using the index k for our function f. So that's going to be k factorial, and it's going to be x to the power of k, times, where is my pointer, times the function g, but I'm not going to evaluate g all the way from 0. I'm only going to evaluate it between k and n. And remember that n will go to infinity. So I'll write the function g, or the summation for the function g, which is just x to the index. And here we're using the index n minus k. So it's to the power of the index. I'll have n minus k here. And that is one way to write this. But the other way, or the other piece to consider, is that in this case, I have x to the k and x to the n minus k, which I could write as x to the n over x to the k, and then these cancel. So I end up with the sum of the sum of 1 over k factorial times x to the n. Now, I have been putting my outer bracket here, and I can technically continue to do that, but it kind of makes sense, if you think about it, to put it here, because I'm actually evaluating this summation for the index k. I'm starting at 0, I'm going up to n. And then I'm taking this entire summation and multiplying this x to the power of n by it. And this is exactly what we got on the previous screen for this product of two functions. So this is kind of a weird one, but it's kind of cool. I'll put a link at the very end of this video to the website where I found this formula. It contains a lot of other formulas as well dealing with Taylor series. And in fact, the page is called Tricks with Taylor series, which I think is kind of appropriate. It looks like a pretty old website. Some of the images are broken, but it's got a lot of really nifty little sort of shortcuts for dealing with Taylor series. And I like it as a resource. So I'm encouraging you, welcoming you to use it in whatever way you see fit. All right, that's it for this one.